Hi class, welcome back. Today we're going to talk about 1.4 continuation and one-side limits. The objectives are to determine continuity at a point and continuity on an open interval, then determine one-sided limits and continuity on a closed interval, and then use properties of continuity, understand and use the interval value theorem. So first, we're going to start by defining the continuity at a point, and then we're going to extend that to an open interval. So if we think about continuity, is basically what you feel continuity means in the sense of in the English language. So it has to be a continuation. Now, if there's a stop, there's a jump. If there is a hole in your path, then that means that the path is not continuous. And so we're going to sort of separate those three cases in this picture. And once we define this in the picture, then we can define them mathematically speaking. So let's first focus on the picture. So in the picture, you see here, if you're walking through this path, this is the path of the function, right? This is the values of the function. And at some point in the value of the function, there's a hole, meaning the function is not defined. So you have to jump to move to the other side of the path, right? So there's a hole, so that means the function is not defined. Now the function here is not continuous at x equals c because the function value is not defined there. So so we have here that is not continuous, right? Because you have to jump there. So f of c is not defined, right? The other case is going to be whenever there's a jump. Now in this case, we're coming from here, and we're focusing in particular here, right? We could talk about this side, we could talk about this side, but let's first focus about this right here. So we're going through this path, and we get to the end of this part. We would actually need to jump to be able to get to the other side of the path. So again, this is not continuous. So this is not continuous, and the mathematical reason for this, or the way we can justify and recognize this in the future, will be by looking at the fact that the limit of the function as x approaches c does not exist. And we can see it does not exist because from the left side, the value of the function is approaching this value, but coming from the right side, the value of the function is approaching a lower value. In other words, they're different values. Then let's move on to the last one. In this example, we end up having that the function, there's a hole on the graph, and we said, well, it's not defined there, the function, but actually it is defined at c. So the function, it is defined at c, but it is not defined in the right place. So, and then also in this case, also the limit does exist because the limit approaches the same value of the limit of the function approaches the same value coming from the left and coming from the right. So these two are sort of even though we are satisfying these two conditions of the function being defined and the function having a limit, it is still not a continuous function because at the end of the day, you actually had there's a pause in this path, and you're not able to do it without it. Another trick that we use often to kind of explain this is that if you use your pen and then you draw and you trace the graph, the value of the graph through the pen, if you have to jump or remove the pen from the paper to get to the other side, that means the function is not continuous. So in the future now, we're going to be looking at these three conditions. Now we're going to put it all together formally to be able to define this. Now, if the function is not defined at a c value, then that's sufficient for us to say that the function is not continuous. Or if we have a function for which the limit does not exist at x equals c, then that's sufficient for us to say that the function is not continuous. Or if the limit of the function as x approaches c is not equal to the actual value of the function at c, then that means the function is not continuous. So you only have to meet one of those criteria to be able to determine that the function is not continuous. So therefore, in order to be continuous, you must satisfy, you must be able to satisfy the following three conditions. A function f is continuous at that point, at a point at c, when the three conditions are met. So let's look at the first one. F of c is defined, meaning that you're never going to have a hole here. You actually have an actual value. The other one is that the value of the function, the limit of the function as x approaches c exists. In other words, you don't have this jump, you sort of have this right there, or that right there. Then lastly, we're saying that the limit, both the limit of the function as x approaches c and the value of the function at c are equal to each other. So in other words, what we're saying here is you're sort of satisfying to be able to have a defined value, and the defined value happens to be the hole that is sort of allowing this path to be able to continue. So if you want to picture it that way, that's fine. And sometimes it just helps to start with a picture in our mind before we can actually be able to sort of really comprehend this concept. But remind you guys that the definition is also very specific, and we can actually extend this definition to an open interval. I remind you guys that an open interval are the values of x, So if you want to define this interval of values of x's from -2 to 3, then we can describe this in parentheses, right? So it's kind of the same. Sometimes we use this notation for a point, sometimes we use it for an interval, and it's usually specified the point this or the interval that. All right, anyway, so a function is continuous on an open interval, in this case open interval from a to b, when the function is continuous at each point in the interval. A function that is continuous on the entire real number line -infinity to infinity is continuous everywhere. Now I remind you guys that the interval doesn't, when it has parentheses, it means it does not include -2 in the interval, and so that's also in this case, because you have a parentheses, that means that the interval does not contain 3. All right, so that was a quick reminder. All right, so therefore we can describe this discontinuation in three cases. So the first one that we saw, that we noticed that it was not continuous, then we can say that this is discontinuous. So in other words, we can say f has a discontinuity at x equals c because it is not continuous there. In the same case here, in this case, we call this a special type of discontinuity. We call this a non-removable discontinuity. Let me compare these two now. I mean, obviously we know that it's discontinuous because you actually have to jump, but what's that about, the removal versus non-removal? What we said about removal and non-removal, what we're saying is that we can remove the discontinuity if we come back and define the function at c by adding this definition, by adding a definition there. We're saying, oh, we can say that f of c is equal to this specific value, and so by doing that, we actually ended up closing that hole, meaning now the function is discontinuous. So you have removed the discontinuity, right? Obviously, you're not gonna do that. I mean, you could if you're trying to define a function. If you have the power to define a function, then you can do that. But it's sort of the idea is that it's removable because all you need is to add a point on the graph to be able to make it continuous, opposed to the next example where if I actually try to remove this discontinuity by adding a point there, it didn't make any change. The function is still discontinuous, right? There's still a jump, so This is non-removable discontinuity. And we can see because you cannot remove it even if you add a point on the graph. This one is also removable discontinuity because you can remove the discontinuation by actually adding a single point. So the trick here is if you can add a point to remove the discontinuation, then that means it is removable discontinuity. Alright, so here are a few examples for us to discuss the discontinuity or the continuity of a function. So we'll begin by the function f of x, 1 over x. We already are familiar with this function. That's sort of the prerequisite of the course, is that we know how to graph this function. Now 1 over x, if you guys want to see it, is sort of this, right? There's an asymptote going around in this axis, and there's another one going around this axis. Alright, so now we can see here that the function will be continuous everywhere, except, remember that we focus on the values of x. That's where we're going to determine where the function is discontinuous. Now we can see here that the function is actually going to be continuous everywhere, right? From the left, right, from negative infinity all the way to approaching 0. Now in this example, there is no value of 0 because we know there's an asymptote there. But if you move to the other side, the right side, we can see that it's coming from the positive infinity, and it is also as we get close, as x gets closer to 0, the function becomes very big. Well, f of x in this case is continuous everywhere except at x equals 0 because there's an asymptote there. So this is non-removable discontinuity because it doesn't, even if we add up a single value, it won't remove the discontinuation. Let's move on to the next example. In the next example, we have x squared minus 1 all over x minus 1. If we graph this, we can kind of see a straight line going around, and we can see that this is discontinuation, but we can remove the discontinuation by adding a single dot. By adding a single dot, that means that this is non-removable. Sorry, removable, my bad. So it's a removable discontinuity at x equals 1. Now notice that it is continuous everywhere, but it is continuous at x equals 1. And to be more specific, it is removable discontinuity. Next example, we have this piecewise function. If we graph it, we notice that the function seems to be continuous everywhere. So all we can say here, the h of x is continuous everywhere, continuous on the entire real number line. Let's move on to the next one. Y is continuous everywhere. So we have the sine function, and we notice the sine function will continue to go on this periodic graph or values forever. So the function will be continuous everywhere. So that's kind of neat. Alright, so now that we have discussed continuity, let's discuss the idea of one-side limit. So the one-side limit means that you have using a limit from one side. When we refer to a limit, we actually refer to both sides. So we need to be more specific if we are dealing with one-side limit. So we have the limit from the right, and that means that x is approaching c from the positive side of the number line. So the positive side means the right side. So the limit of f(x) equals L. So if we see this picture here, as x is getting closer to c, the value of the function, the size of the function, the value of the function tends to get the same value as L. Now if we come from the left side, that means you have to be coming from the left side of c. So you're coming from the left side of c, and we see that the value of the function now tends to decrease to be able to get the same size of L. Right. So now that we have discussed both limits, both sides, now we can discuss the limit of the next example. So if we think about it, when we apply the limit to one side, we tend to get a little confused because now we have this little plus there and this minus. They're not powers, they're not anything, they're just more like notation. It just tells the reader or reminds them that we're taking the limit from one perspective, from one side, and then we're saying that this is coming from the right. So nonetheless, it's still a limit, so we should be able to try the same tricks that we done before. That means that we replace x with the value of 0. So you replace x with the value of 0, then you have the nth root of 0, and then the nth root of 0 is 0. So we end up getting 0. So let's try the next example. Find the limit of f of x, where f of x equals to the square root of 4 minus x squared as x approaches negative 2 from the right. So if we are approaching negative 2 from the right, that means, and for this function, that means that we can actually try to plug in the negative 2 in here. So let's see what happens. If we plug in negative 2, we get negative 2 squared, that gives us 4. 4 minus 4 is 0, so we get the square root of 0, which is 0. So basically what we're saying is that the limit of the square root of 4 minus x squared is, as x approaches negative 2 from the right side, is equal to 0. And then we can kind of see the picture here. As x gets closer to negative 2 from the right side, the values of the function tend to go down, down, and down. Alright, so we need to discuss one of the special functions that we haven't focused that much in our previous classes. This is known as the greatest integer function. The greatest integer function, what it does is actually it rounds. Now it doesn't make the regular type of rounding that we're used to. It's actually always rounding down. So it's always a round down. So round downs to the nearest integer. So let's look at the first one. So let's look at the greatest integer of 2.5. Well, excuse me. So 2.5. I mean, if we would have if we would have rounded this, then we would have rounded up. But like I said, we don't round that way. We round in a special way. We always go down, right, to the nearest integer. So the nearest integer of 2.5 going down is 2. Now the next one here, it's sometimes gets the students sort of confused. So remember that we always try to find the lowest integer, right? So if you have negative 3 and negative 4 and negative 2 and your number is here, then sorry, that's not it. Alright, so if we have negative 2.5, then you have to round down, right? You have to round down. So going this way, that's rounding up because the number is getting bigger. So you have to round down. So therefore, you're gonna go to this direction. So the number will be negative 3. Alright, so next example, we'll talk about the continuity of the greatest integer function. So let's first find the limit of the greatest integer function f of x. There's a few problems in the homework, so please make a note of this type of function. So find the limit of the greatest integer function f of x equals the greatest integer of x as x approaches 0 from the left side of the and the right side. So here we have a graph, right? I mean, we have a graph, but usually we're not able to see a graph. Or is it now we don't have the proper technology to be able to do that, but nonetheless we can always make a table. Now remember that I said before is that we have developed a few techniques, but nonetheless the most basic one that we already know how to do is the table. The table will always work. It's just very, very hard for us to actually work with. But nonetheless we're gonna come to 0 from the left side, so that means the x values are coming from the left side. So there'll be like negative 1, negative 0.1, negative 0.01, negative 0.001. And so every time you plug in a point here, well, we have to round down. So what's in the nearest greatest integer? That means going down will be negative 1. Same thing for this one, negative 1, negative 1. And at 0, we are not determining that. But if you're coming from the right side, as x approaches 0 from the right side, then we have the values of x will be 0.1, 0.01, 0.001, which are going to round down to 0. So we end up having all these just horizontal lines, and these are horizontal lines. All right, so that's so we notice here they both approach to different values. So what we're gonna say here, because the limit from the left is not equal to the limit on the right, the two-sided limit does not exist. The next theorem makes this more explicit. So finally we get the formal definition of the existence of a limit. So if we have a function and we let c and l be any real number, the limit of the function f of x as x approaches c is L if and only if the following are true, meaning that the limit of the function as x approaches c from the left side must equal to the limit of the function as x approaches c from the right side. So those need to be the same before we could actually discuss further. All right, so let's move on to the next example. The next example, we're going to talk about the definition of continuity on a closed interval. So far we have sort of discussed the open interval, but now we have the tools to be able to define the closed interval. Now basically it's half of the chunk of this chunk of definition. It actually has to do with the main function. So a function f is continuous in a closed interval AB when f is continuous on an open interval AB, right? So we already know that part, but we also need to check that the limit of the function as x approaches a from the right side is equal to f of a, and the limit of f of x as x approaches b from the left side is also have to be the same as f of b. So the function f of f is continuous from the right at a and continuous from the left of b. Alright, so let's try the next example. The continuity of closed interval. Discuss the continuity of f of x equals to the square root of 1 minus x squared. Now we can show that this is continuous on an open interval. Then we can just show that the limits of the endpoints also exist. So therefore, this should be fine. So we'll start by observing what kind of function do we have. That way, it kind of gives us a few hints. Well, this is a radical square root function. And in order for the square root function to exist, we just have to make sure that the inside of it is positive. So what we're going to do is that we're going to use some basic algebra from college algebra, which says that take the radicand, set it greater or equal to 0, factor them out, and then find the zeros. So let's find the zeros of this. The zeros of this is whenever this is 0, which happens at 1 minus x equals 0 and 1 plus x equals 0, which gives us 1 and negative 1. Followed by that, we're going to have to find where the function domain is, and so we're going to make a number a sign chart, which we did in pre-calc in college algebra. So at x equals negative 1, we end up getting a 0 for the function, that hence the word zeros. When x equals 1, we also get a 0, but when we got a left side information, we end up getting that we're gonna get a negative number, a positive, and a negative here. So we have to check these numbers, and then these numbers and these numbers. So let's check in the negative numbers. And I apologize for this. I kind of my eyes were a little bit tired here. So all right, so let me just get a little more energy here, and thank you for your patience. All right, so to check the domain of this function, right, we just have to plug in numbers on this side, this side, and this side. If you do, you're going to realize that the function, the value of this is negative, the value of this is positive between those two, and the value of this is negative on this side. So the function, this 1 minus x squared is greater or equal to 0 for only numbers between negative 1 and 1. So that means that when you add the square root on it, the domain of this function will be -1 to 1. So the domain is this. Now all we have to do is check that the endpoints limits are good to go. So coming from the right side, as x approaches -1 from the right side, so from the right side, all we have to do is, remember, it's just a limit, so we can always try to plug it in, right? So plug in the -1 and then see what we get. So we get +1, 1 minus 1 is 0, so we get the square root of 0, which happens to be the same as f of -1. That means if you plug in -1 here, you're gonna get also 0, which we should, right? But then we try the 1 from the left, the limit of the function as x approaches 1 from the left side, and then again we're gonna plug in the 1 there, and we're gonna simplify. We get 0. We get to do a square root of 0, which is 0, and that happens to be the same as f of 1. So it seems that the definition is being satisfied. So we can conclude that f is continuous on the closed interval -1 to 1. Alright, so there are a few properties of continuity that we want to discuss. If b is a real number and f and g are continuous at x equals c, then the functions listed below are also continuous at c. That means that if you multiply a continuous function with a constant, then the resulting function will still be continuous. If you multiply two continuous functions, then you're going to still get a continuous function. If you add or subtract two continuous functions, you still have a continuous function. If you divide two continuous functions, then you still get a continuous functions, with the exception that whenever the bottom is equal to 0. That means that this division will not be continuous. So in the bottom part, we're going to summarize some of the most relevant continuous functions. The first one is the polynomial. The polynomial happens to be an expression composed of coefficients, variables, and powers. So as long as all the powers are whole numbers, and the coefficients can be any real number. So this means that this is all these are all good to go, right? These are going to be continuous everywhere. The rational function here is going to be continuous everywhere except where the denominator is 0. The radical expression will be continuous everywhere except where the radicand is 0 and the index is even. Otherwise, if it's odd, then it's going to be continuous everywhere. So trigonometry, the functions are continuous everywhere. So we can combine all these functions with the techniques from 1.11, and we can kind of create more functions, right? So we can say here that the function f is continuous because x is a polynomial and sine is a trig function. So when you add two continuous functions, we get continuous. Tangent is continuous on its own domain, so we multiply by a scalar, you still have continuous. The numerator is continuous and the denominator is continuous, so this is going to be continuous except whenever the denominator is 0. And the next ones are also continuous, and these happen to be composite functions. So continuous and continuous, so we end up getting continuous on all three cases. Not everywhere, but we get continuous on the under domain. So f is the next example. We have g is if g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x is continuous at c. So this one is a little more tricky because you have a function instead of a function, and sometimes that gets confused to the students. But let's try these new examples. So let's describe the continuity on the interval for this using the intervals of these functions. So what we're going to do is we're going to define the continuity of each of the functions. Now we have to sort of know the context or the sort of background of definitions of these functions. So we know the tangent of x is sort of unfamiliar for everyone, so we try to rewrite it as sine and cosine, and that gives us usually a better understanding of the function. Now we know because this is a quotient that it's going to be discontinuous whenever the denominator is equal to 0. So overall, the function is continuous, but is undefined whenever cosine of x equals 0. So f of x tangent of x is undefined at a particular value. So whenever the cosine is 0, which happens at pi over 2, 3 pi over 2, and it just repeats, right, because it's periodic. So we're going to say that where x equals pi over 2 plus n times pi, where n is an integer, then the function will be undefined. Other than that, for other points, f of x is continuous. So f of x is continuous on open intervals where we exclude the pi over 2. And so here's an example. Next example, we have g of x. We have a piecewise function, and we have on one of them we have sine of 1 over x, and the bottom is 0. So for 1 over x, it's we know it's continuous everywhere except x equals 0. Now, since sine is actually continuous everywhere, but in this case, since the limit of x does not exist at x equals 0, then g of x is not continuous at x equals 0. So here we have to be a little careful, but we notice that the limit of f of x does not exist at x equals 0. And I think I meant here g of x. So let me fix that. Alright, for h of x, and then we can see here a picture, right? So here we see the picture. Oops. The picture tells us that the function is continuous, but then the limit does not exist here, and then it passes through that. So therefore, this is not continuous there at x equals 0 because the limit does not exist. For h of x is continuous everywhere. This is very similar but different to the previous problem. The reason why this is continuous is because we're able to really squeeze this part of the graph into almost a line. The problem with this is that we were having verticals, and then here it seems like we have a chance to be able to throw some desk. I meant desk, I mean in discrete theorem. Sorry about that. Alright, so intermediate value theorem. Alright, so the last part. The intermediate value theorem is very useful, and you guys will be tested on this a few times. So we're gonna make sure we understand this. So f(x) is if we know that f is a continuous function in a closed interval from a to b, where the values of f of a is different than the values of f of b, and we know that k is any number between the f of a and the f of b, then there is at least one number c between a and b such that f of c equals k. So notice a few things. I want to make sure you guys recognize that we are given 3 conditions for us to satisfy. First, f needs to be continuous, so that's rule number 1. Rule number 2 is that the f of a and f of b are different, and that k happens to be between those f of a's and those f of b's. Then we can conclude that there is a c between a and b such that f of c equals k. So let's throw this example here. And if you guys notice, this is sort of what I want you guys to think about when you guys are doing your problems, especially in the test. You guys have to justify your answers. So an application of the intermediate value theorem, we're going to use the intermediate value theorem to show the polynomial f of x has a 0 in the interval between 0 and 1. What do I mean by a 0? That means that it has a root, it has that means the function will pass through y equals 0. So here we go. First of all, is the function f of x continuous? And the answer is yes. This is clearly a polynomial, and therefore it is continuous everywhere. Now you should invest yourself on recognizing polynomials. They're very easy to identify. That means they're just composed of variables, pluses and minuses, and exponents. So the exponent of your x's must be whole numbers. They cannot be negatives, they cannot be fractions. So that's the only rule of thumb. So it is continuous. Now can we check the second condition, meaning the f of 0 is different than f of 1? And it is. One of them is negative 1, the other one is 2. So they are different. Rule number 3 is the number 0, because we're trying to see if we have a 0 between f of 0 and f of 1, and the answer is yes, because f of 0 is negative 1 and f of 1 is 2. So therefore it must be between those two. Now because we satisfy condition number 1, condition number 2, condition number 3, and by the intermediate value theorem, there exists some value c in the interval 0, 1 such that f of c equals 0. And we kind of see this picture over here. It kind of makes sense, right? If you have 2 points, here, and the function is supposed to be continuous, meaning that you can get from here to there without stopping, without jumping, that means eventually you need to cross the zero value, which means is the x-axis. Eventually you have to pass it. So it forces for the existence of this value c that would be between those 2 points. Anyways, let's move on to the next one. Oh, actually that was it. So that was intermediate value theorem. I hope you guys find this helpful. Please go over this again and make sure if you guys have any questions, please let me know. Thank you.